Okay, so I'll just rewrite what it says on the sheet. And these will only take a minute to do all of these. They're not really using much different than we already know. Okay, so one thing, if you look at these sets, we've got the union rather than the intersection. The intersection would be the center, and we don't have the center. So when we're not given the center, we use the formula. Remember there was two formulas? So, it didn't ask for this, but there's a big long list. I'm sure it's going to, so we're just going to figure it out right now. And I knew to do this because this looks like a Venn diagram type question, and we're missing the center, that intersection. Whenever you're missing the center, you need this formula or the big long one if there's three sets. So the union is 0.6, A is 0.26, and B is 0.41, and we don't know this one. And if we just rearrange this, bring that over to that side, becomes plus, and bring that 0.6 over there. We'll get the intersection. .07. All right, so if we need it, we could find it. We could also find what's not in A and B, because if we drew the Venn diagram for this, here's A and here's B. We now know the center, and then we can work our way out. What's A is 0.26. We've already got 0.07 in there, so we subtract 0.26 minus 0.07 is 0.19, so that circle adds up to 0.26, and then 0.41 minus 0.07 for B is 0.34, and then what goes out here? The whole thing has to add up to 1 for a probability, so we would add this up. Well, A is already 0.26. I need to add the 0.34. That adds up to 0.6, so we're missing 0.4. And now, really, we can answer any question. Some of them will require a formula, but I'll show you that when we get to it. So if you know it's going to be a Venn diagram question, there's a bunch of questions with it. You might as well just draw the Venn diagram before you start, because you probably need it anyway, right? A lot of times on a test, I'll say draw the Venn diagram. To help you out. And so I can mark that, because then if I see your Venn diagram's wrong, but you answered the right section, like whatever number was in there, I can give you a mark for knowing that. Not for knowing the Venn diagram, you'd lose marks for that, but if you at least answered the right sections, even if your numbers were wrong. If I don't ask for the Venn diagram, I have no sort of part marks to give if you don't draw it. Okay, so A, the probability of the universal set, always 1, nothing to even look at. The probability of anything happening, that's what that's saying. And B is the probability of nothing happening, is 0. Okay, so highest and lowest. C says the probability of A intersection B, which we found, 0.07. D, the probability of A prime. So you can look at the Venn diagram and do it, anything that's not in A.
So like 0.34 plus 0.4?
Right, 0.34 plus 0.4. The other way to do it would be 1 minus the probability of A. 1 minus 0.26. That'll give you the same number as just adding these two, 0.34 and 0.4. Right, either way. E, probability of B prime. Same thing. You could add up the stuff not in B, 0.19 and 0.4, or You could do 1 minus the probability of B. This way's probably safer in case you did your Venn diagram wrong, and you were given A and B itself, right? Yeah, but it also, if you look back up at the Venn diagram, it didn't match your answer, you could also say, oh, I must have messed something up. 0.41, so this would be 0.59. F, probability of A prime intersection B. This is where the Venn diagram would be useful. So this is saying what not, and if you weren't sure what this was saying, you could draw it. A prime intersection B is the stuff not in A, but is in B. Not in A, but is in B, is this section. So when you look up here, you see that it's 0.34. G. What's that saying? Not A and not B. So 0.4. That's asking for the outside. And you could draw it again and see where it is if you weren't sure. A prime union B prime. This is a little trickier. I personally would probably use Damoff Theorem, which says you can take the primes off like that if you flip the sign.
If you try to draw it.
If you try to draw it, so you would say, union is easy if you try to draw. So if you had A prime union B prime, you can draw it. If it's all union, you can do it all in the same picture. You don't need to erase anything. So A prime is everything outside of A. Okay, so there's A prime. Cool. This means add to it. Don't erase anything. Just add on top of it everything in B prime. So that's what the picture would look like. Just the center not included. And if you look at this, this is A intersection B, which is the center not. All right, so either way. So not the center. So if we knew it was not the center is 0.07. You could add these three, or you could just say 1 minus point.
Yeah. So really, you don't need to know any formula other than the ones to find the centers, right? Like if you could do it by drawing, you're never going to ask, like, what's the formula for this?
There is none.
No, but like when you said
you
here? Use, yeah, like
I wouldn't,
like
yeah.
Flip the sign, that kind of thing?
No.
Okay.
But there is a formula, and that's in the next four.
Okay.
Yeah.
No, I was just kind of...
So there is one, yeah.
To, like, work it through it, or if...
Oh, yeah. No, I don't ask for the formula, so if you can figure it out without a formula, then you can just do that. Okay. So the next ones use the conditional probability formula. Which was the probability of A given B is the probability of A intersection B over the probability of B. So you do need to remember that formula. There's not very many. There's the one to find the intersection, the union rule. This, and I guess this is a formula, like if you want not B, then you can 1 minus B, that would be the other formula.
Yeah. I guess it's logical when you wrote it out and said this represents the center, but like it doesn't come with you.
Yeah.
For me anyway.
So here, which is the first one? I. Probability of A given B. So you would say, okay, this is the probability of A intersection B. Oh, I just wrote this same question. This was the formula, which we didn't need to change anything for this one. So the probability of A intersection B, we found the intersection is 0.07. And the probability of B, 0.41. 0.07 divided by 0.41. You can't leave it like this. You do have to. Yeah. You don't need to keep more than 2 decimals. It doesn't. They're probabilities. They're not exact anyway. J, probability of A prime given B. So the same thing. You say, okay, A prime intersection B over the probability of B. So just write the formula out. Did we find A prime intersection B? We did. It was 0.34, and the probability of B is 0.41. We found that in part F. So A given B prime, A intersection B prime over B prime. So whatever's given that comes after the line, that's the one that goes on the bottom. Otherwise, it's just the intersection of the two over the one that's given. And whatever's given is after the line. This one I don't think we found, did we? So this is saying in A, but not B. In A and not B. So it's in A, but not in B. That would be this piece. So that's 0.19, if you look up at the graph. And B prime we did find was 0.59. And this one is the opposite of the first one? The intersection's the same. B intersection A or A intersection B is the same. That's 0.07. But this is over the probability of A instead of B. So this is saying, given that you're in the A circle, what's the probability that you're also in B? Yeah. So this is out of A, which is 0.26.
So when it's written like that, like P of B given A, what is the actual question asking? Like if you were to put in words?
Well, this is saying like if you were given that you're in A, what's the probability of getting B?
You're also in B. So like,
so
it's really only asking for the center part?
No, because your chance is different. The center is not 0.07 of A. It's a different portion of A.
Okay.
So it's 0.27%
right,
of it.
Dividing by it.
Yeah,
Okay,
yeah.
I'm just trying to
If you're in A, the numbers are for the overall, they're not for just A.
Right.
Like this is the 100% of being in A.
Right. Okay.
Which are now different numbers. So if you want to know what chance if you're in this,
so wouldn't it be like 0.07 divided by 0.07 plus 0.19?
yeah, exactly.
Okay.
Which is
So
what we did.
What you're doing?
Yep.
Okay. I just didn't think of it, like I just thought, like memorize the formula and then fill in the blanks, but if you get, it makes sense now. Sorry.
No, that's good. Okay, so then 9. So 9 says, in a class with 2/5 women and 3/5 men, 25% of the women are business majors. Find the probability that a student chosen from the class at random is a female business major. So so in math, so women and men are not two different circles on a Venn diagram. Okay? You're one or the other. in math, okay? So this is a two-circle Venn diagram. We're asking about business majors and whether you're male or female, right? You don't want to put 3 circles because they're not going to give a question like that, all right? So here we're saying, like, if you want to say that women are one circle and business majors are another. Okay, so for example, so it says a class with 2/5 women and 3/5 men, 25% of the women are business majors. Now, there's also mixed up fractions and percent, but you could change it all to decimals, and then they're more comparable, right? So they're saying the probability that you're a woman in the class is 2/5. So what is that as a decimal? 0.4. And the probability that you're a man would be what? 0.6. And then what's the other number they give? A woman and a business major is 0.25. Right? Oh, no, that's wrong. That's wrong. I didn't read close, so that's wrong. Read the question and tell me why that's wrong, or think about why that's wrong. Yeah, it's saying 25% of the women, and the only reason I noticed that I was wrong was when I read the question, not when I read that, because the question says what? Find the probability that a student chosen from the class at random is a female business major. Well, what's the difference between being a female business major and being...
a woman and a business major?
Right, they kind of sound the same, so that's not, so that, this is not what it was giving. What it was saying is more like this. So let's draw a tree diagram to illustrate. So here's the women, and 2/5 of them, or 40%, are women, and 3/5, or 60%, are men. Do you agree? Of the women, of these, 25% are business majors.
So this is the same thing?
No. No, you don't need base. Every tree is not base theorem.
Every tree?
Yeah. And these would be non-business majors. What percent are not business majors? Not that it's asking that, but you could actually answer that. If 25% of these women were business majors and 75% are not. Men, we don't know. It doesn't give us that information, right? So it didn't tell anything about that. And then it's asking for the probability of being a woman and a business major. So what we know is, we know the probability of a woman is 0.4, and we know the probability that if, given that you're a woman, okay, the probability that you're a business major, given it's a woman, is 25%. So how can we find this? It's kind of the formula backwards. Like we have the formula and it has 3 pieces, and we're given 2 and asked to find the other. So the formula for conditional probability is the intersection over this one. Right? And we're given this and that, and we're asked to find the intersection. So we would actually just multiply them. If you cross multiply here, like probability of B given W times the probability of W is equal to the intersection. So this is 0.25 times 0.4. So they're saying, if a random person walked in the room, what's the chance that they're female and a business major? Well, there's less females than there are males, first of all, so that's why it's so small. Right, because a random person walked in the room, the chance that they happen to be both female and business majors, which are the two smallest of all of these groups. So 0.1, or 10% chance. Okay, and probably 10 is similar to that, so let's read this one carefully this time, not make a mistake.
So basically, if you're using the word given, you just kind of go with the conditional clause.
Yeah, and I try not to word them so confusing on tests, but you can ask me a question if the wording is weird, if you're not sure. As long as your question doesn't require me answering how to do something, I can explain it better. But I try really hard on tests to be really clear, okay, but sometimes it's hard. So I try not, in the book, they're a bit harder to read sometimes. What the given part is, the way they word it, is not obvious. I usually try to put the word given in the question so you know that that was a conditional probability. Okay, so 10, the probability that John will do his math homework is 0.8. The probability that he will do his history homework is 0.7. And the probability he'll do both his math and history homework is 0.9. Are the events do his math homework and do his history homework independent? Independent. What does independent mean? Yeah, well, one doesn't depend on the other, right? So the numbers you see there obviously add up to more than one.
Yeah, but wouldn't it be separate, or wouldn't it be not wouldn't it be dependent because the likelihood that he'll do both is higher than the likelihood that he'll do one or the other?
So this is the actual test for dependence. So dependent, or independent, sorry. So something's independent if when you say and, like doing this and that, and you multiply them, and it gives you the same as the intersection, then they're independent. So, and most of the questions we'll see are actually going to be independent. Everything we're going to see after this page is independent, really, because we're going to say most of the time one doesn't depend on the other. Okay? But here, if we take his numbers, so we have math is 0.8, history is 0.7, and math and history is 0.9. Yeah, I don't think this question makes a lot of sense if you're thinking about it. So the intersection, is the intersection equal to both of them being multiplied? No. 0.8 times 0.7 is what? 0.56? How can you explain this? I guess if he starts his homework, he feels more likely to do more homework, but if he doesn't start it, he doesn't get going, so he's more likely to do both if he starts one. I mean, you can kind of think of it that way, right? You know, if you start a project, you're more likely to finish the project, and if you keep procrastinating and not starting something, right? So that's probably what this is about, although that's a really weird question. And I don't test on dependence and independence, but we should show that. So whether something depends on the other. So he's saying the probability of doing both homeworks is 90%, which probably means, it's high. These ones are high independently, but, yeah. It's 11. An experiment consists of drawing two numbers from a jar that contain 5 numbers, 1, 2, 3, 4, 5. One at a time without replacement. So we're going to draw 2 without replacement. So you can't get the same number twice. We're going to keep it. A, find the probability that the 3 is the first number given that the sum is 7. So here we're given the sum is 7. So how can the sum be 7? 5, 2, or 2, 5. Remember we talked about that the order matters. If you're drawing 2 at a time, you could either get the 5 and then the 2, or the 2 and then the 5. So we know one of these 4 things happened. So what's the question asking? The probability that the first number is a 3, given that the sum is a 7. So how many of these have the first one as a 3? 1. So the probability is 1 out of 4. If these are only the 4 options, you're told that the sum is 7, then you have 1 out of 4 chance that the first number was a 3. The second one says the first number is a 3 given that the sum is 6. Oh, this is interesting. So the sum is 6 would be 1, 5, 5, 1, 2, 4, 4, 2.
And you wouldn't be able to do 3 and 3
because, right, without replacement, so there's no 3, 3.
So if it was with replacement, you'd be able to do?
Yeah.
Yeah.
So what's the answer? 0. 0 to 4 if you want, or 0, just 0. There's none. If you know that the sum is 6, then you do not win. There's no chance that you had a 3 as the first number. That's the impossible event. Okay, so what we're going to do is skip Bayes' theorem and go to combinations and permutations. Because that's, I think, more important. Okay. So, I did 3 lectures on that. We're not going to do that much, so we'll kind of pick and choose. What I'll have to do tomorrow is go into the practice questions and cross some of them off, okay? So, because I'll cross off anything that's Bayes' theorem or anything we don't get to tonight. So there'll be a few things. We'll just do more important stuff. Okay, so counting principles. So the first is the multiplication principle. When you have a series of choices to make, then the number of total possibilities is the number of choice 1 times the number of choice 2 times the number choice 3, etc. So we already did the multiplication principle. We said, like, if you're rolling or tossing a coin, it's 2 choices, 2 options the first time, and then 2, and you multiply those. And I said anything like that's in like that last example, we only were talking about a few options, but if we wanted the total number of possibilities, we could list them all out and count them. Or we could say, well, there's 5 pieces of paper, there's 5 choices for the first draw, and then we reach in and there's 4 choices for the second draw, so all together there's 20 different ways that we could list all these numbers that could happen. The one with the 2, the one with the 3, the one with the 4, the one with the 5, the 2 with the 3, the 2 with the 4, the 2 with the 5, right? If you listed them all, you'd get 20, okay? So that's multiplication principle, okay? Then the second is permutation. So there's a button on our calculator for that. And there's a formula. Does everyone know what factorial is? That exclamation point? It's n times n minus 1 times n minus 2 all the way down 3, 2, 1. So for example, 5 factorial is 5 times 4 times 3 times 2 times 1. It's that number multiplied by all the numbers under it. Okay, where does this pop up? Well, just like the slips of paper, if you just kept pulling one out until they were all gone, you have 5 choices the first time, then there's 4 pieces of paper left, you have 4 choices, then 3, then 2, and then you pull the last one out. So that's if you're ordering a whole bunch of things, okay? Permutation is actually just a extension of the multiplication principle. I don't actually use it very often. The only time would be like if you were picking 50 pieces of paper or 50 names out of a draw, you would not want to type in your calculator 50 times 49 times 48 times 47 times 40. You don't want to type all that, so there's a button for it. And that's really what the permutation does. I'll show you when I would use this as opposed to this, but it's basically the same thing. You're making a bunch of choices, you multiply the numbers, but this will give you something a little different. So I'll show you what it is in a second. We'll do an example, but we'll write the third one down as a combination.
Do you mean like factorial is the same, or permutation?
Permutation and multiplication principle are the same thing. You're just multiplying a bunch of numbers. The difference here is they go down. 5, 4, 3, 2, 1. Here they don't have to. Like you could be picking a pen and then eraser. So, and there's 20 pens to pick from, and there's 4 erasers, so 20 times 4. The numbers don't go down necessarily, multiplication principle. I'm going to give you examples of all. This one is, they always go down. It says you're dividing, but you're not, okay? Let me explain it first and give you an example, okay? So the formula will just work itself out. You'll see exactly what I mean. Okay, so just wait. There's only 3, so let me write the third one, and then I'll give you examples of all 3. So the last one is combination. There's a button on your calculator for that. Some people write it this way, if you've seen that before, but I don't. Okay, so here there is an important difference with this one. Order is not important. With both multiplication principle and permutation, you're doing the first task and then the second task. So that's all talking about putting something in an order. That's what number 1 and 2 are. This one is not an order. What's the difference? If you were dealing cards to play a game of cards, and then you know you move the cards around in your hand, the order that you were given the cards doesn't matter. You still have the same cards in your hand. But if you were, so order being important is more like you're picking someone to win first prize and someone to win second prize, and the order matters. Okay, so we're going to show the difference between that, but just we want the formula, okay, and the three different possibilities. So here's the three possibilities, and I said really there's only two because multiplication and permutation are kind of the same thing. So there's either a combination or a permutation, which is done either of these ways. So now we're going to see examples of what the difference is and how to solve them. Okay? Ready? So, there was a question in my son, he's in grade 5, in his homework that was the multiplication principle. And it was this. Suppose you have five shirts and 3 pairs of pants. How many different outfits do you have? That's assuming you can put them all together. So, it's multiplication, but let me show you why. If you were to list them all out, okay, so say you've got your 5 shirts, let's call them A, B, C, D, A, B, C, D, E. There's your 5 shirts. So that's your first choice. You pick one of those shirts. And then when you pick a shirt, how many choices do you have next? 3. Your pants, we'll call them 1, 2, 3. Right? So how many outfits are there possible with shirt A? 3. Shirt A with pants 1, shirt A with pants 2. There's 3 possibilities. What about B? 3. What about C? 3. D and E. Altogether, you've got 3 outfits 5 times. This is 5 times 3, which is 15. That's the multiplication principle. Now, you can't use permutation for this because the numbers don't go down 5, 4, 3, 2, 1. But I'll show you an example that does work. So that would be, and so they do that in grade 5. They don't call it anything. They just want you to know that you have to multiply. Right? And they're practicing multiplication. They were just word problems with multiplication, and that's what they were. So saying there's 5 groups with 3 each, or 3 pants each with 5 possible shirts, 3 times 5 or 5 times 3, either way would give you the right answer. Okay, so let me add a little harder one. Okay, so say in the mall at Christmas time they do gift wrapping. You can go and get your presents wrapped. Okay, so let's say there's a gift wrapping station. Gift wrapping station at the mall. Okay, so you need to walk up to them and you pick a paper. So let's say there's 4 different papers. If that was all, and you walked up to them with your gift and say, can I have this wrapped with that paper? There's 4 choices. So right now there's just 4 possibilities. Nothing to multiply yet. Let's add a ribbon. So you could pick one of the 4 papers, and then you look up on the wall and say, well, I want this paper with that ribbon, right? So that would be a second choice. So ribbon. Let me make it complicated. There's 3 colors in 2 widths. So how many different ribbons are there? 6. There's like a wide red and a narrow red, a wide blue and a narrow blue, or whatever, green and white, whatever the colors are. Probably red, green, and white for Christmas. Maybe gold or something. But that's 6, okay? So now how many choices do we have? 4 times 6. 24 possibilities now. But wait. Could you say, I just want that paper and no ribbon? Could you do that?
Yeah.
could you maybe say, can you put a ribbon around this, but I don't want it wrapped?
Yeah.
So it's not really 24 choices. What do you think?
So could you just not wear a shirt? Or not wear pants?
It didn't give you the option. It said how many outfits. You're picking a shirt and a, right?
Okay. Because if it did, would that be permutation then? No?
Oh, still multiplication principle.
Yeah.
But, yeah. Okay, so just keep that in mind that you don't have to pick something, okay? What about cards? Maybe they have gift cards. 10 different cards. Okay, so first of all, we're saying this is 6, not just 3 or 2, okay? So let's change that to a 6. Okay, so A, if we choose one paper, one ribbon, and one card, how many ways can a gift be wrapped? So we're doing 3 choices: a paper, a ribbon, and a card. A paper, a ribbon, and a card. You agree? 3 choices. How many papers? 4, ribbon 6, card 10. So 240 ways. I would say they're probably not equally likely in the real world because some of them might not go together, so you know, you might not choose some. That's just the probability of it, though, but we're not talking about that yet. Okay, B. If we must choose a paper, so they're saying you can't walk up and ask just for a card. We're not going to give it to you. Okay, so if you must choose a paper, but need not choose a ribbon or card, how many ways?
So in the first one, you're assuming you have to choose one of all 3?
Right, which I said.
Okay.
Right? If we choose one paper, one ribbon, and one card, yeah. So if we must choose a paper but need not choose a ribbon or card, how many ways? So paper, ribbon, card. So how many papers are there? 4. How many ribbons are there?
7.
Right, 7. It's 6 or none. None is a choice. So you can choose a ribbon, but you don't have to. So instead of it being 6 ribbons to choose from, it's really 7, which the 7th ribbon is no ribbon. So 7. And then, so what would cards be?
11.
Right. 28 times 11? What's that, 10? 3. You know how to multiply 11s in your head? I taught my son that yesterday. Do you want to know? You can't really say no when someone says that, right? Your math prof asks you if you want to know how to multiply 11s. You just say, okay, fine. Teach us 11s. Well, you know 11 times 2, 3, 4, 22, 33, right? But a 2-digit number. So I'll give you an easy one first. Say we wanted 11 times 23, okay? Don't do it out. You just take the 2 and the 3, you put them at the end, and add them together and put it in the middle. That's it. Now, there's a problem. This was a problem. I had to think about what I was doing. And I wrote 28 over there so I could look at it. So times 28, what happens that the problem is? If I put the 2 and the 8, if you add them together, it's 10. So what you do is you still put the 0, but you add 1 to this. So 308. It's like you carry the 1 over to the next digit. So if we wanted like 99 times 11, it'd be 9 and 9. But if you add 9 and 9, it's 18. Yep. pretty neat. So 2-digit numbers by 11 is actually pretty easy, even if you have to carry over. The other one only ever goes up by 1, so it's just you change that. And yeah, it can be 2 digits. I think 3-digit numbers work the same, but there's just more carrying. It's harder to do in your head without writing down. Okay, so I just said 28 times 11. I said, oh, 28, oh, that's 10, so 308. Okay, C. If at least one ribbon, paper, or card must be chosen, how many ways? No. What's the difference? The other one said we must choose a paper. Here it's not saying, it just says you have to choose one thing. You could just choose a card, or you could just choose a ribbon and not a paper.
So it wouldn't be like, it would be like 308 or this or this? Like
I would start over. So paper instead of 4 would be 5. You could choose no paper. So 5 times 7 is 35 times 11. Let's do our trick. So that adds up to 8, so 385. But what's wrong with this?
You can't choose none of all.
Right, so how would we adjust that number?
Subtracted by 1.
Mm-hmm. Take off the option of nothing, because you're not going to walk up and say, can I have nothing? Right? That's not really one of the choices. So we should subtract 1, which is the nothing of all 3, right? So really it would be 384. So sometimes you count more than what you have and take off what you don't want. And that's sometimes easier. Actually, a lot of times in math, it's easier to do the opposite of what they're asking. So another sort of classic question we use the multiplication principle for would be something like how to arrange letters in a word. So it comes down to just being a choice question again. You've got 4 letters, and you want to choose one to write down first, and then you want to choose the second one to write down, and then the third, and then the fourth. So you were just rearranging these letters. So you have how many choices for this first spot? 4. There's 4 letters to choose from, so you write one of the 4 down, and then you've written 1 down, so you've got 3 left, 2, and then 1. That's a 4 factorial. If you want to put it in your calculator that way, you can. There's a factorial button. On mine, it's right above the 4, and it's in orange, so I actually hit the orange button here, second function, and that's saying 4 factorial is 24. It's not really too long to type it in. Okay, just like that, but sometimes it might be. If there was 50 letters, then you wouldn't want to type in 50, 49, and so on. You'd want to do it quick. Yes, this is a permutation. It's actually 4p4, which means this. The total to choose from and here, this is the number you want to arrange. So, for total, arrange all four, will work out to 24 if you put it in your calculator. Actually, this gives me a good, so the formula was n factorial divided by n minus r factorial. If we put this in n factorial, so n is the first number, so 4, and then subtract them, what do we get? 4 minus 4, which is 0. 4 factorial divided by 0 factorial. All right, I'm telling you this is the same thing, but you can't divide by 0. But 0 factorial, this is like the 0 choice. It's actually 1. It's 1. 0 factorial works out to 1, not 0. It's just a rule, but it's kind of, if you think of it that way, it's like, it's the choice of choosing nothing. It is one choice. So 0 factorial, if you put that in your calculator, 0 factorial, 0 factorial, you get 1 as your answer. 0 factorial is equal to 1. So this is also 24. That's how a permutation works. But you don't need the permutation because you're just writing out the numbers and multiplying them. That's what I was saying. The permutation part, you actually don't need. It is the same thing as the multiplication principle, where the numbers go in descending order. So you can use it if you wanted to, but you're never going to do that. When you know the numbers are 4, 3, 2, 1, you're either going to type them in or you're going to put it as a factorial. You're not going to do this.
So it won't ever be like those questions.
There could be, because there's like 365 days of the year to pick from, and we want to pick, 10 of them. That's not too bad. 365 days and 364, 3, 2, 1, right? But as a permutation, that would be 365p 10. Out of the 365 days, pick 10. So that might be quicker to type in than 10 numbers that are, but you don't need to do this. You could type in 365 times 364 times 363, 2, 1, right? But it's shorter. But we're going to do it in a second. That we'll write that a bunch of times, but it's really, if you're picking stuff that's going in descending order, then you can always use the permutation button for that. Okay, so like this was going in descending order. There was 4, and we wanted 4 things, so 4p4. This would be, there's 365 things to pick from, and we want to pick 10 of them. Or if we wanted 365 things, and we wanted to pick 50 of them, we wouldn't want to type that in. So you would need this formula for that. But the number's too big anyway. It wouldn't work in your calculator. So, okay, how many ways to arrange the letters in the word Emma? So how is this different than the word math? It doesn't have as many ways because there's 2 M's. So if we switch the 2 M's, it's still the same arrangement, like it doesn't look any different. We call that indistinguishable if you can't tell them apart. So this has